Hello everyone, welcome back to the channel. In this video, I am going to discuss the efficiency and losses of the transformer. If we have to define efficiency in general, efficiency is defined as the ratio of output to input. And if we talk about the transformer, in case of transformer, the output is the electrical power output and input is the electrical power input. So in case of transformer, the transformer efficiency is defined as power output upon power input. The power input can be written in the form of power output and losses. So efficiency can be written as power output upon power output plus power losses in transformer. So for detailed discussion of transformer efficiency, we must need to understand the different type of losses which occur in the transformer, and then we can move on to the efficiency. So let's discuss the transformer losses first. So in case of transformer, different types of losses occur. First one is core loss. The core loss means the losses which occur in the core of the transformer. So in case of core of the transformer, we have two different type of losses: hysteresis and eddy current loss. Then there is copper loss. Copper loss is the actually loss which occurs in the primary as well as secondary winding of the transformer. So basically this is I square R loss. The name given to this is copper loss since the winding of the transformer is made up from copper. Then we have dielectric loss. Dielectric loss is the loss which occurs in the insulation, but these losses are actually negligible, so we will not consider them in detail. Also, another loss which is negligible is stray loss. The stray losses occur due to leakage flux in the transformer. Again, they are negligible. So the dominant losses which occur in the transformer, which we need to discuss in detail, they are the core loss and copper loss. The core losses, they are further consisting of two different losses. Core losses are denoted by Pi. They are also known as iron loss. Since core is made up of iron or some alloy of iron, so that's why the name given to them is iron loss. They are denoted by Pi, and these losses are actually sum of hysteresis loss, pH is hysteresis loss, and PE, that is eddy current loss. These both losses occur in the core. The hysteresis loss, they are dependent upon the material which we use for the core, frequency and maximum flux density. So this is a formula for calculation of hysteresis loss, where Kh is a constant, or it's known as hysteresis coefficient, and its value depends upon the material. Bm is the maximum flux density. This is maximum flux density, and F is the frequency. Eddy current loss, which is denoted by PE, are given by KE F square Bm. KE is again constant dependent upon material. F is the frequency, Bm is the maximum flux density, and here this constant N over here, it is in the range of 1.5 to 2.5 depending upon the material. So what we see in the expression of hysteresis loss and eddy current loss, both are dependent upon frequency and maximum flux density. Now from the EMF equation, we can actually find the expression of this maximum flux density in terms of voltage. Now if you remember the EMF equation, which I had covered in the previous videos, it was given as 2 pi f root 2 pi f n phi max, which is equal to 4.44 fn phi max. So you can check this video in the link which is available in the description box if you haven't checked it earlier. We know that phi max is equals to B max into area of cross section. So from here V, which is equal to 4.44 Fn phi max, it can be written as B max to AC, or B max will be equal to V upon 4.44 Fn AC. Since frequency is constant, number of turns are constant, area of cross section is constant, so what we see that the expression of hysteresis loss over here, it will get modified as pH, which is actually equal to kh into F into Bm raised to power n. This will get modified as kh into F raised to power minus 1 minus n to V by n. Since all other terms are constant, so they can be incorporated over here. So basically the hysteresis loss, that is proportional to the voltage, as well as the eddy current loss, which is equal to Ke F square Bm square. Now this can be written as Ke into V square. So both these losses, they are dependent upon the voltage. Since the voltage, the input voltage and the frequency, they are kept same in the transformer, so these losses remain same irrespective of the loading. Whether the transformer is loaded or not loaded, core losses will occur in the system. Even if the transformer is fully loaded or half loaded, irrespective of the load, core losses are always constant. So core or iron loss, they are constant, or we can say they are independent of load. Now moving on to the next loss in the transformer, which is copper loss. Copper loss is the losses which occur in the primary as well as secondary winding as I square R loss. So copper loss, they will be denoted by PCU. PCU will be equal to I1 square into R1, means I square R loss occurring in the primary winding, plus I square R loss occurring in the secondary winding. Secondary winding current into secondary winding resistance. So these can be written as I1 square into RE1, where RE1 is the equivalent resistance of the transformer transformer equivalent referred to primary side, or this one can be also written as I2 square into RE2, where RE2 is the equivalent resistance referred to the secondary side. So here we need to use the equivalent circuit. So if you haven't seen the referred equivalent circuits in the previous video, you can check the link of the video which is available in the description box. So what we see over here, the copper losses, they are dependent upon current I1 and I2. So I1, I2, the currents, they are dependent upon the load. So what we can say that copper losses, they are variable losses and they are dependent upon load. Now coming back to the efficiency, the efficiency of transformer, which is equal to output power upon output power plus losses. Now losses are iron loss and copper loss. The power output of the transformer is output voltage into output current into power factor. So efficiency can be written as V2 I2 cos theta upon V2 I2 cos theta plus Pi plus the copper loss. Since we have written current I2 for the power output, we will express the copper losses in terms of secondary side current. So it will be I2 square into Re2. Now what we see over here, the efficiency of the transformer, that depends upon the power factor as well as on the load. Now if we assume that the power factor is constant, we can write it as cos of theta 2. So if we assume that power factor is constant, we can find out the condition for maximum efficiency. From here we can calculate the maximum efficiency condition. Now to calculate maximum efficiency, since we have assumed that cos theta 2 as constant, the only variable which is left over here, that is I2. It's dependent upon load. So we need to differentiate this with respect to I2 and equate that to 0. And equate this to 0. Now when we differentiate, so we have V2 I2 cos theta 2 plus Pi plus I2 square Re2 into V2 cos theta 2 minus V2 I2 cos theta 2 into V2 cos theta 2 plus 2 times I I2 RE2, and in denominator this V2 I2 cos theta 2 plus Pi plus I2 square RE2 square. Since we need to equate this to 0, so we can write V2 I2 cos theta 2 plus Pi plus I2 square RE2 into V2 cos theta 2 is equals to V2 I2 cos theta 2 V2 cos theta 2 plus 2 times I2 RE2. Now what we have, V2 I2 cos theta 2 plus Pi plus I2 square RE2 is equals to V2 I2 cos theta 2 plus 2 times I2 square RE2. This terms cancels out with this one, or what we get, Pi is equals to I2 square to RE2. So I2 square into RE2 is actually copper loss. So the condition for maximum efficiency is that when copper loss and iron losses they are equal, at that time efficiency of the transformer is maximum, or what we can say, that when the constant losses are equal to the variable losses, at that time the efficiency of the transformer is maximum. We can write it like constant loss is equals to variable loss. Now this copper loss, it is not necessary that this is the rated full load copper loss. It can be the loss at any current rating. It depends upon the transformer. It can vary from transformer to transformer. So now what we can do, we can actually calculate the fraction of load at which the losses, the efficiency of transformer is maximum, or the copper loss and variable losses they are equal. Let's say the full load copper losses are denoted by PCUFL, that is rated full load copper loss, which is known from the short circuit test. We can calculate them from the short circuit test. Pi is a constant loss or iron loss. Rated full load copper losses means the losses which occur in the winding at the rated current of the transformer. So PCUFL, they will be equal to I2 full load square into RE2. I2FL means full load rated current of the secondary side, and PCU, that we know it is I2 square into RE2. Let K is the fraction of full load. Now what we mean by K is fraction of full load, it means I2 is equals to K times I2FL. 50% load means K is 0.5, 75% load means K is 0.75, 80% load means K is zero point 0.8, and so on. So this is what we mean by fraction of load. So PCU can be expressed in terms of full load current by using K I2 is equals to K times I2FL. So PCU will be equal to K square I2FL square into RE2. For maximum efficiency, PI and PCU, they must be constant. PI, it should be equal to K square I2FL square into RE2. I2 square FL into RE2 is a full load copper loss. So K is the fraction of load at which efficiency is maximum. It can be calculated as P under root of Pi upon PCU FL. So this is how we can calculate the fraction of load which will give us the maximum efficiency. Also what we have written that efficiency is V2 I2 cos theta 2 upon V2 I2 cos theta 2 plus Pi plus PCU. We can write the efficiency at any load or at any fraction of load. Let's say you have to calculate the efficiency at 80% of the full load. So this I2 will be equal to K times I2FL. So we can write this as V2 I2FL cos theta 2 upon K times V2 I2 cos theta 2 plus Pi plus K square PCU FL. So using this expression, you can calculate the efficiency at any fraction of load. Also, one thing I need to mention over here is about the rating of transformer. The rating of transformers is expressed in kVA and primary to secondary side voltage. So for example, we can have 4 kVA, 220 to 440 volt single phase transformer. It means 220 is the primary side voltage, 440 is secondary side voltage. Its kVA rating is 4 kVA. From here you can calculate primary side current as well as a secondary side current. Primary side current can be calculated by 4000 upon 220. Similarly, secondary side current can be calculated 4000 by 440. So the current which we get from here, that is actually full load current. These are the rated current of the transformer. So in any case we have to calculate the efficiency and rating of transformer is given like this. Then we can use this V2 into I2FL as 4 kVA, that is into 4000. So this expression can also be written as K times S cos theta 2 upon K times S cos theta 2 plus Pi plus K square PCU FL, where S is the apparent power. So in next video, I will discuss the tests which are conducted on the transformer so that we can calculate the equivalent circuit parameters as well as we can calculate the efficiency from the test data only. If you find this video helpful for you, please consider sharing it with others and also consider subscribing to the channel. Thanks for watching the video.